Okay, so before going into the part 2 where we find for the velocity, I just want to highlight something that is pretty not interesting, but rather than I also need to tell myself in the future also. Alright, is that to determine the life of the bearing, alright, it's talking about when you finish rubbing away the whole layer, this 300 micrometer of the surface, the oxide, I would say, the white metal, alright, is being removed. So in order to determine the life, you have to say that after the shaft until all the thing has been removed, which is what we have been calculating all along. We have been calculating all along using the amount of volume, alright, where the length or whatever the area, or it's based on the amount of the length of this thing, alright. So it's talking about the amount of volume when every of the white metal is being removed. So how much is the life, how much revolution or whatever thing that it is in order to remove all the coating. So this is one hell of a thing that you should take note of. But nonetheless, let's come back to the velocity thing, because we need to solve for the velocity, if you remember. So we have already gotten the sliding distance as the meter, alright, the s in terms of meter. So in order to solve for the time taken, alright, it's talking about meter per second. I should say that it's talking about the sliding distance divided by the linear velocity of your shaft, and you'll get your time. Alright, it's because this is in terms of meter. So in other words, meter divided by meter per second, you'll have meter times second meter, cancel, you'll get second. So this is what we are trying to achieve over here. Alright, so so therefore, in order to solve for these things, you need to take note of the 20 rpm. So the omega Young modulus, the omega angular velocity is equals to 2 pi number of cycle divided by 60. Okay, in order to find your angular velocity, this is the equation. So the 20 is the number of revolution per minute. Alright, this is in terms of second already. Alright, angular velocity is meter per second. Alright, so therefore this is another equation you need to put inside your pocket. Okay, so we have 40 pi over 60 because this is 20 now. Alright, 20 times 2 is 40 times pi, so what do we have? 2.094 radian per second. Okay, so the omega is in terms of radian per second. Okay, so you change from rpm to radian per second. Alright, so this is 2.094, and in order to change your angular velocity to linear velocity, what do we have? The equation is linear velocity is equals to angular velocity times the radius. Alright, so the angular velocity is 2.094. Our radius is what? Radius is actually the diameter of the shaft. The radius of the shaft. Okay, and take note it's in terms of millimeter, so you're going to change to meter. Since everything is in terms of meter, you would have 30 times 10 to the power of negative 3 meter. So you would have, maybe I should calculate myself also, double check. You will have 0.0628 meter per second, which is a linear speed. Alright, so then the next thing now, alright, is taking your s, your sliding distance, divided by your linear velocity, you'll get your time taken. And therefore, I think you get what I mean already. Most probably you're off this video already. Okay, anyway, so velocity 0.628 is equals to, what do we have? We would have 5.2 times 10 to the power of 6 s second. Okay, or in other words is 1440 hours. Okay, and this is only the equation part that you need to talk about. So we have finally determined the life of the bearing, and the key equations over here is three equations, like this omega, this linear velocity conversion, and taking the sliding distance and divided by the velocity. These are all cheat codes, like nowhere coming out. Okay, and then the last part of the questions itself, it did ask that the next one is, how do you assess the wear if there is no more white metal, the sacrificial metal, that the hard surfaces of the shaft and bush. But meanwhile, I just want to also talk about the what's that called? White metal. White metal itself talks about the oxide layer, I should believe. okay, which is this page, okay, deals with the oxide layer. Alright, presence of metal. I don't know whether is it purposely. I don't think it's purposely. It's more on the micro welts, I think. But anyway, just need to take note of this value 0.2 in case if anything happens. Alright, and yeah. So how do we assess the surfaces of the shaft and the bush? So how do we assess the wear? So it deals with talking about the amount, talking about the different wear. The abrasive wear, alright. There's 5 types of wear actually. There is adhesive wear, alright, the abrasive wear, fatigue wear, corrosion wear, and erosion wear. Okay, yeah, that's all. So most probably there is 2 types of wear in this scenario. There is adhesive wear, and adhesive wear you need to take note of the definitions. Alright, adhesive by the name itself is this is the hardened material, this is the softer material. Alright, so if you were to put onto over here, okay, and when the adhesive means that the softer material, alright, will adhere onto the hardened material, okay, and then after that when you turn, the whole thing will be removed, and this is being explained over here as you can see. Alright, where am I? So you may need to also draw this type of diagrams, I think. Yeah, I don't think it's over here plus 2 marks, but in the future if there is more marks then you need to draw. That's what the lecturer has to say, I think. Yeah, anyway, what's over here is when the adhesive bond is stronger than the base material soft. So when the bond itself, when it's very strong, then it will start to remove, and this is called the adhesive wear. Okay, and therefore we are using the archard wear law to solve for these things. Alright, and abrasive wear is because when you remove this thing, alright, when this thing happy remove, there may be some debris, there may be some chips falling off, and these chips falling off will be kept between another surface. Okay, so yeah, so maybe kept between this surface. Okay, and therefore when you rub against, when you start to rub again, when the next round of the shaft is turning, you're gonna have certain abrasive that happens. Okay, this is where the hard particle comes in. Alright, so use good lubrications, use of hard materials, whatever it is, and yeah, so you need to articulate between them. That's what he says. So the debris will start in the abrasive wear, that's what he says, and the adhesive thing. So you need to write down in your words the definitions. What I just say you write out in the words lah. Maybe I should write out also lah. Anyway, due to adhesive bonds stronger than the soft material, which is the adhesive wear, or the adhesive wear may happen and debris may fall out due to this, which may also result in abrasive wear. Alright, and a long time due to Archer's wear law, because of the volume thing, alright, the bushing may also be wear off since the white metal has been sacrificed. So this is not for lecture, but yeah, if you think it's good then you just take lah. But it's for my own future also. So I think that's all, and yeah.